So delta H, the heat of reaction, can be calculated as we just did using Hess's law if we have a series of chemical reactions that we can add together and where we know the delta H is. We can also calculate it from what are known as standard enthalpies of formation. So delta H is the change in enthalpy, and we're always looking at changes in enthalpy. Where is zero enthalpy? Well, it's not like zero speed or zero distance. That's a little easier to define. Zero speed is even a bit relative, because are you comparing that to our surroundings here on this section of the Earth? Or are you comparing it to the sun? What's your relative comparison there? So what we can do here is we can define zero enthalpy to be something that's convenient. Why not? We do this with other things. We measure changes in altitude relative to sea level. Why is sea level zero altitude? Because it's convenient, right? Sea level is approximately the same all over the globe. Now, is that a really, really fixed point? Not really, because the tide comes up and down and the icebergs melt and things go up and down a little bit. But it's a good point of reference. So we're going to measure changes in enthalpy relative to the enthalpies of pure elements in their standard states. So what does that mean? Standard state is the state of a material at a defined set of conditions. So these are the conditions. If we're talking about a gas, we're talking about the pure gas at 1 atmosphere of pressure. If we're talking about a liquid or a solid, we're looking at the pure substance in its most stable form at 1 atmosphere of pressure and the temperature of interest, which is usually 25 degrees Celsius, room temperature. If we're looking at a substance in solution, then we're looking at a solution concentration of exactly 1 mole per liter. So that's what we've defined as standard states. So the standard enthalpy change is the enthalpy change that we observe when all the reactants and products are in their standard states. And so we take that delta H and we put this degree sign after it, and that indicates that this is occurring at standard states. We can add a subscript F onto this and call this the standard enthalpy of formation. So this is the enthalpy change for a reaction where we're going to make 1 mole of the compound from its constituent elements in their standard states. Because we've defined the pure elements as being zero enthalpy, we know that for pure elements in their standard states, their standard heats of formation are 0. So we find these heats of formation in a table such as this. This one's in Chapter 6. There's a longer one in the appendix for your textbook. You may need to look these things up when you're doing homework problems. I would encourage you to look in the textbook rather than trying to Google it, because there is some variance in these values depending on where they were calculated, and sometimes Google will give you a slightly off answer. Mastering Chemistry is basing all of its answers on these values. So if we look here we've got bromine gas and bromine liquid. This is bromine, atomic bromine in the gas state. It has a heat of formation of 111.9 kilojoules per mole. Liquid bromine, as a diatomic molecule, has a standard heat of formation of 0. That tells me that's the standard state for bromine. Its most stable form is Br2, and at room temperature it's a liquid. So that's its standard state. Here's carbon. Carbon, two common forms are graphite and diamond. They are both solids. But graphite is considered the most stable, the standard state, and so it has heat of formation of 0. The diamond, carbon in the diamond form, has a small heat of formation. So we can look at all of these different compounds, and they're organized here by different elements, like sodium. Come on, pointer. Here's sodium solid, and here's sodium in the gas state. It's a little strange to think of metals in the gas state, but you can do that. You can get metals into the gas state. Now, is that how they normally are? No, it's not how they normally are. Sodium, in standard conditions, is going to be a solid. You can make it into a gas, but then we have a heat of formation. It's going to involve 107.5 kilojoules per mole of sodium to get it into the gas state. Standard enthalpy of formation, also called standard heat of formation. We talked about the difference between enthalpy and heat and decided that it didn't really matter for our purposes. Standard enthalpies of formation for elements are 0 because we decided that to make things easy. For most compounds, their heats of formation are negative, which means that when you form those compounds from their elements, energy is released. In terms of elevation, that's like being below sea level. Because when you let go of something, does it float up or does it fall down? Most things fall down. And if you're out on a ship and you hold a bowling ball off the side and you let go of it, is it going to stop at sea level? No, it can go below sea level, right? It's just going to keep going down until it hits something solid. So the way we figure out what the heats of formation or enthalpies of formation for different compounds are is we write a chemical equation that shows them being made from their elements in their standard states. Now, this does not mean that you can actually make the compound this way, but that doesn't matter because this is a state function, and so exactly how you get there doesn't matter. So if we look at methane, methane is CH4. At room temperature, it's in the gas state. So we can look up the heat of formation for this. It's minus 74.6 kilojoules per mole. We can write an equation showing the formation of 1 mole of methane from its elements in their standard states. So methane contains carbon and hydrogen. So the reactants are going to be carbon and hydrogen. Now, we have to be careful to pick the ones that are the standard states. So go back to that table. And we're looking at hydrogen. There's H, the element, and H2, the molecule. Sorry, atoms and element. Atoms and molecules. H2 is the standard state. And we should know that because hydrogen is one of those diatomic elements. So H2 gas is the standard state for hydrogen, and we already looked at carbon. Its standard state is solid graphite. So we can write this as carbon in solid graphite form plus hydrogen, H2 in the gas state, making methane in the gas state. Then we balance the chemical equation. What's kind of funny about these is we always balance them so our product has a coefficient of 1. We're looking at the equation to make 1 mole of the product. And sometimes that's going to require that we do half a mole of something in one of it as a reactant, and that's okay. So when writing these standard formation equations, if you're not sure what the standard state is, look it up in that table to see which one's 0 for that element. The definition requires that 1 mole of compound is made, so the coefficients of the reactants might be fractions. Here it was a 1 and a 2. What's important is that our product has a coefficient of 1. So let's write a formation reaction for carbon monoxide. So carbon monoxide is CO, it's in the gas state. First we identify what are the different elements that are in that compound. There's carbon and there's oxygen. And then we have to figure out what are the standard states for those two elements. So for carbon, we talked about this already, it's the solid graphite. And for oxygen, it's O2 in the gas state. That's the regular form, the standard form of oxygen. So now we have our reactants, and this is our product. We need to balance this equation. Normally, we would take this O2 and say, oh, well, we need 2 of these, then we need 2 of those. For these formation reactions, the product has to have a coefficient of 1. So we're going to say, well, we're going to take 1 mole of carbon and half a mole of oxygen, and that's going to make 1 mole of carbon monoxide. You can't really have half a molecule of oxygen, right? But you can have half a mole of oxygen molecules. So all of this is in moles. And the heat of formation, you look it up. You don't memorize heats of formation. The only ones you should remember are that if it's an element in its standard state, it's 0. If you're doing an exam and there seems to be some stuff missing, you've got these elements, and maybe you're not sure if they're in their standard states or not, if there's no information given anywhere and their states match up with what we know about the periodic table, it's probably just 0. Remember, on the periodic table, anything where its element symbol is in black on that table is a solid at room temperature. So the standard state for all of those elements would be solid. Anything that's in red is a gas. Anything that's in blue is a liquid. We won't see any of the white ones on exams. And then we should know the 7 diatomic elements. Yes?
The half of the oxygen, just in a way of balancing with the CO, right?
Yep. Yeah, we're putting this half here just so we can balance the equation while having a coefficient of 1 on our product. So we need half a mole. It's not that we're going to have half of an egg, but we can have half a dozen eggs, right? So this doesn't necessarily make much sense if we talk about it in terms of molecules and atoms. But if we talk about moles, we can definitely have half a mole of oxygen molecules. Any other questions? So let's practice. Write equations for the formation of sodium chloride solid and lead 2 nitrate solid from elements in their standard states. Include the values of the standard heats of formation. So I'm going to write the reactions first, and then we'll look up the numbers. So for the first one, A, our product is sodium chloride. I'm going to start by putting that over here on the product side, sodium chloride. I have an arrow here. There's 2 elements, right? Sodium and chlorine. So I'm going to write sodium and chlorine. And we need to know their standard states. We could go look in the table, but we could figure this out. So sodium's a metal, right? And what color is its symbol on that periodic table on the wall? It's black, meaning it's a solid. Is it one of the 7 diatomic elements? No, none of the metals are. So the standard state for sodium is just the element as atoms as a solid. How about chlorine? That's diatomic. And what's the state? It's a gas. So we could find that looking at the table, but we should know that also from basic information in the periodic table. So then if I'm going to balance this, I can't put anything here. I need 1 mole of sodium chloride. So how can I balance this? 1/2 of a mole of chlorine. Everybody okay with that? And it says include the values of delta H, standard heat of formation. Well, for that, we're going to go look in the table. Sodium chloride, it says minus 411.2. Minus 411.2 kilojoules. That the table says kilojoules per mole, and it would not be incorrect to put per mole here. This is 1 mole, so whether you write that or not, it is that many kilojoules for 1 mole. Any questions? Let's do the second one. So here we've got lead to nitrate as our product. How many elements are in that? There's 3, right? Lead and nitrogen and oxygen. So we've got Pb, and we have N, and we have O. What's the standard state for lead? It's a solid. It's a metal, so it's going to be a solid at room temperature. What about nitrogen? It's a gas. Is it diatomic? Yes, it is. So N2 gas. I have to move this over. I didn't leave enough space. Plus, and what about oxygen? It's also a gas, and it's also diatomic. So I'm looking at the elements in their standard states. It's their most stable form. This is what I'm making out of them, and now I need to balance the equation without putting a coefficient over here. So there's 1 mole of lead in this, and I've got 1 mole of lead over there, so that's great. Here I've got nitrogen. In the nitrate, there's 2 of those, and I have 2 nitrogens over there, so that's nice. How many oxygens are in 1 mole of this? 6 moles. We have 6 moles of oxygen in this 1 mole, so here, to get 6 moles of oxygen, I need a 3. Okay? And then I need the got lost. I need to look up the heat of formation. Yeah, it's not on there. I think, yeah. So this is from the back of your textbook. There are more compounds here, and here there's lead on the lower right side there, and we can find PbNO2 solid minus 451.9. So any questions? Yes. Yeah, I write that down wrong. 451? Okay. They say there's 2 things that you lose when you get older. One is your memory, and I can't remember what the other one is. Thank you. Okay. Any other questions? In a way, writing these sorts of reactions is easier because you don't have to think about charges on the ions or what is that ion, the nitrate, do I leave it together or not? For these, you're going to pull everything apart into individual elements. Let's see. Okay. So, that standard heat of formation corresponds to making a compound from its constituent elements. Right? We've got the elements, we make the compound, standard heat of formation. We look it up in a table. What if we take the compound and break it down into its elements? That's writing the equation in the reverse direction. We just change the sign on delta H, right? So we can use these heats of formation to estimate heats of reaction. What we're doing is we've got reactants that are compounds, and we're going to imagine pulling those apart into their elements in their standard states, and then taking those elements and making the product. So pulling things apart is the opposite in sign of the heat of formation, and making it is the heat of formation. So we can write any reaction as the sum of formation reactions, or the reverse of them. So that stuff we did with Hess's law, where we took the 2-3 reactions and figured out how to add them together, we can do that using formation equations for anything. And what we imagine doing is, we've got a couple of reactants. They're like little Lego structures, and I'm going to pull them apart into individual blocks. And then I'm going to take them and I'm going to put them back together. So we can look up in a table how much energy it would be to take the compound apart into its elements. And we can look up how much it would be to make the product from its elements. And then we can just add those things up. So to make a kind of scary looking equation out of this, the standard heat of reaction is the sum of the heats of formation for all the products minus the sum of the heats of formation for all the reactants. We're subtracting this because we're taking the reactants apart, and so that's negative. Forming the products is the same as the sign of delta H, F. NP here is the coefficient for that reactant or product. Because if you tear apart 2 moles of something, you're going to have twice as much energy change. So that's the overall idea, which probably is really confusing right now. So let's look at this and see if we can make it make a little more sense. So here we have a chemical reaction. We have methane burning in the presence of oxygen. It forms carbon dioxide and water. And we want to know what is the energy change associated with this. What's the delta H reaction for this? And instead of doing an experiment and trying to measure this, we can look up numbers and calculate it instead. So what we're going to do is we're going to imagine taking this methane and pulling it apart into the elements, carbon and H2. And we're going to oxygen, O2, that is the element in its standard state. So we don't have to do anything to that. Then we're going to imagine making CO2 from carbon and oxygen in their standard states, and making water from hydrogen and oxygen in their standard states. So here is where we're starting. These are the reactants listed here. So we're going to imagine taking the methane and decomposing it, making it into carbon and graphite and 2 hydrogens. We looked at that formation equation earlier. If you look up delta HF for CH4, it's minus 74.6. This is plus 74.6 because it's going in the opposite direction. Does that make sense? So now I've got carbon, hydrogen, oxygen. I've got all of these elements in their standard states. That's like 0. So in my elevation change analogy, what I'm going to do is first I'm going to go down to sea level from wherever I was, and then I'm going to go up or down from there, and I'll compare the two segments to find out the overall change. So here are my elements in their standard states. Then I'm going to imagine making carbon dioxide. So that's going to take one of these oxygens and this carbon to make CO2. I look up the heat of formation for that. It's minus 393.5 kilojoules. And then I'm going to take what's left. I've got 2 moles of hydrogen and a mole of oxygen, and those can be combined to form 2 moles of water. Formation of 2 moles of water is the heat of formation of water times 2. And then I'm going to add everything together. So I had to invest 74.6 kilojoules, and then I got back 393.5 and 483.6. I add those all together, and overall it's negative 802.5. Does that make sense? Just do it and make sure the math is correct. 74.6 minus 393.5 minus 483.6. 802.5, negative. We can also do it looking at combining these formation equations for the different compounds. We've got methane as one of the one of the reactants. This is the formation equation for methane. But instead of forming methane, we're taking it apart. Right? So this would be opposite in sign. We can look at the formation equation for carbon dioxide, taking carbon and oxygen to make carbon dioxide. We are forming a mole of carbon dioxide, and so we've got that heat of formation is the minus 393.5. Then we're forming 2 moles of water. So 2 moles, and that becomes 1, and this is 2, and this is multiplied by 2. For adding equations, we're going to take this one and write it backwards. Oops, not CH3. So I took that first one and I wrote it backwards, and I changed the sign. Now we're going to take these 3 equations and add them together. I've got carbon, solid graphite on the product side and on the reactant side, so those cancel. I've got 2 hydrogens here, and I've got 2 hydrogens over there, so those cancel. What I've got left then is the methane. I've got oxygen here, I've got CO2, and I've got water. So I've got CH4 plus 2 O2, making CO2 plus 2 H2O. you see it? No? I can take these three chemical equations and add them together. If I have something that's the same on the reactants and the products, those cancel out. So that's why I crossed some of them off. Here I wrote this equation backwards because instead of forming methane, we're actually taking it apart. And so this equation, methane going to carbon plus hydrogen, then I can add that to these other ones and the equation comes out. So that's thinking about this in terms of Hess's law. Then there's also that kind of scary looking equation with the big summation signs. That actually ends up being a little simpler. So the heat of reaction, standard heat of reaction, we're going to take the heats of formation for the products. So making 1 mole of CO2. There's a 1 here. 1 mole of CO2. Well, the heat of formation for that is 393.5. It's negative. So minus 393.5 kilojoules. And I'm making 2 moles of water. So plus 2 times the heat of formation for water, minus 241.8. So those are my products. That's the energy for forming my products. Now I'm going to subtract the heats of formation for the reactants. When I subtract these, what I'm doing is I'm looking at the energy to take them apart rather than put them together. This is already put together, I'm trying to take it apart. So I take the products and then I subtract the reactants. So I've got 1 mole of methane, and its heat of formation is 74.6 kilojoules per mole. And I've got oxygen. What's the heat of formation for O2 gas? 0. It's an element in a standard state. So 0. So then I take this negative number plus 2 times this negative number, and then I subtract this, and I end up with the same value. Minus 802.5 kilojoules. Any questions? Let's do one. The thermite reaction in which powdered aluminum reacts with iron oxide is highly exothermic and rather spectacular. So we've got the reaction there. Use standard enthalpies of formation to find the standard heat of reaction for this thermite reaction. So it's good to understand that we can write formation reaction equations for the compounds here, and we can take those reactions and we can add them up and get this overall reaction. That's actually somewhat tedious to do. We can also do more of a thought experiment and say, well, we're going to take our reactants. Oh, look, this is already an element, so we don't have to worry about that. We're going to take this compound, we're going to take it apart. How much energy is that going to release or absorb? Well, that's the heat of formation for that compound. We look it up. And then we're going to imagine making this from its elements in its standard states. So that's the heat of formation for this. And the heat of formation for iron, which also happens to be 0. So the standard heat of reaction for this. Remember, delta is final minus initial, almost everywhere. Final minus initial. So the products are the final, so I'm going to take the enthalpy of formation, heat of formation for Al2O3 plus 2 times the heat of formation for iron. Those are my products. Then I'm going to subtract 2 times the heat of formation, for aluminum, and the heat of formation for the Fe2O3. Does that make sense? It's a little bit like, okay, well, I start with these things and I'm going to return those to the store and buy these instead. Or I'm going to sell this stuff and buy this stuff. So I'm going to get rid of one and I'm going to get the other. So this one that I'm getting rid of, those are negative. The one I'm getting, that's positive. So I need to look these things up. Oh, nope. Okay. They're back here. Al2O3 solid minus 1675.7. And I need iron. Fe2O3 is minus 824.2. So this heat of formation for Al2O3, I just looked that up. It was minus 1675.7 kilojoules per mole. How many moles of that do I have? 1 mole, right? So I'm multiplying by 1 mole. And what's the heat of formation for iron? It's 0. It's an element. So there's my reactants. My products. I'm going to subtract my reactants. I've got 2 times the heat of formation for aluminum. It's an element, a 0. 2 times 0 is still 0. And the heat of formation for the Fe2O3, I looked that up, negative 824.2. Yeah, what about those signs? The sign switching happens here when we're subtracting. So we look at the heats of formation for the reactants. We're subtracting those from the products. This isn't how the book presents it, but you could just take this, the heats of formation for these, change their signs, add the heats of formation for the products without changing their signs. You'll get the same thing. Yes?
So this is basically just a simpler way to do it than the previous problem.
This is just a simpler way to do it than writing out all those equations and trying to figure out how to add them together. Yeah. We have to talk about that because that's why we can do this. But we don't actually have to do that for these things where we've got heats of formation. So you always need to be careful when you've got negative signs. Just kind of trust your calculator. So I'm just going to do minus the negative 1675.7 minus negative 824.2. And this comes out to be negative 851.5 kilojoules. So the standard heat of reaction for this equation is minus 851.5 kilojoules. This is the energy change associated with making 1 mole of this, with 2 moles of this, using 2 moles of that, and 1 mole of that. Any questions? There's one more example here. Chemical hand warmers. So those chemical hand warmers produce heat when they're removed from their airtight plastic wrappers. The oxygen from the air is then able to combine with the iron, making Fe2O3. Calculate delta H for this reaction and calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. So the standard heat of reaction for this, we can calculate that by taking the heats of formation for the products and subtracting the heats of formation for the reactants. So I've got 2 moles of iron 2 oxide, iron 3 oxide. That's my only product, and then I'm going to subtract the heats of formation for the reactants. I've got 4 times the heat of formation for iron and 3 times the heat of formation for oxygen. So this is really 2 moles of that times the heat of formation. That happens to be the same compound we used in the previous example, so minus 824.2. And in the table it says that's kilojoules per mole. The units work out here because we're actually multiplying by the number of moles that we had. What's the heat of formation for iron? 0. How about O2? 0. These are elements in their standard states. So that one's just 0 and this one's 0. So that one kind of came out a little easy, huh? So negative 824.2 times 2. Negative 1648.4 kilojoules. So that is the standard heat of reaction for this equation. Okay with that? Sometimes the calculation ends up being really simple. So that's the first part. Calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. So this is stoichiometry with energy. We've got our heat of reaction. This amount of energy is for the molar amounts given in this equation. So this is for 4 moles of iron, for 3 moles of oxygen, for 2 moles of product. So we're going to use dimensional analysis here. We're going to start with grams of iron. We're going to go to moles of iron. And then we can go directly to kilojoules of energy. So 15.0 grams of iron. I want to convert that to moles of iron. I'm dividing by grams of iron. And then I've got kilojoules up here and moles of iron in the denominator. Minus 1648.4 kilojoules of energy for how many moles of iron? For 4. I need a 4 down there. And then for iron, grams to moles, 55.85. It's just off the periodic table. Grams is 1 mole of iron. We have 15.0 divided by 55.85 times negative 1648.4. And so this is giving me negative 442.4 48.7 kilojoules. It says calculate how much heat is produced. Is negative 442 produced, or is the change negative 442? The change is negative 442. 442.7 kilojoules of energy are produced. So when we're answering this question, because the direction of energy transfer is indicated in the question, then we don't want to include a sign on our answer. It's like saying, well, how much did that cost? Oh, it cost me negative $50. What does that mean? Does that mean someone paid me to take it? Or was that just a negative 50 on my bank balance and I'm just being weird about it, right? 'Cause we don't say that, do we? Oh yeah, that cost negative $50. We don't do that. So this is the same thing. Energy's like money. If we say it's produced, then we don't need a negative sign. If it says, well, what's the change? What was your net income last year? That could be negative. Hopefully not. Could be positive, up, down. What kind of profit did your business make? Well, actually, we had a loss in the third quarter or whatever, right? So they're just the change. We have to have a sign. But when there are words that indicate the sign, then we leave the sign off. Any questions?